Hello ladies and gentlemen, I'm John Round. This is who's speaking. I've been in the industry for about 40 years and I've held different positions and worked with quite a few well-known and probably some not well-known companies in my time. And currently I'm the treasurer of the Midland section of the CIBD. Right, the bones of brewing. I do some lecturing at the University of Nottingham. For the students there, I like to give them an idea of why certain materials are used over others. And this particular one is aimed for hopefully students that are going to be sitting the CIBD exams in May, June this year. So there is a sort of a slant towards student information as opposed to nice to know information, if you know what I mean. So one of the things I've always tried to point out to them, that the brewing industry has always been quite a progressive industry, and you can exemplify that by containers. I mean, originally they were wood and they moved to aluminium. Then they moved on to stainless steel, and now you got plastic. But you do get some reverses, because a few years ago you used to get steel cans, and now the majority are aluminium. So to some extent, as I say, there's a reversal. But what I'm trying to put out today is the changes in material choices and usage over the years, and understanding why certain materials are used as opposed to other ones. And perhaps the information you get today, you have an opportunity to look around your brewery to look at the various materials that are in use. So, looking at these are the materials that I'm going to be discussing, some in reasonable detail and others just glancing, because let's put it this way, you don't come across many slate fermenters in this day and age, but I'll put them in there for completeness. With the first one, stainless steel, that is the main material of construction in modern breweries throughout the world, and I will be sort of dwelling on the types of stainless steel. So without more ado, let's move forward. Stainless steel comes in numerous grades. I mean, if you pick up a stainless steel stockist's brochure or on his website, the range is just mind-boggling. I've put up here the elements associated with how to identify them, and I'm still using the old grade ASTM, which stands for the American Standards for Testing and Materials. I use these grades 303, 304L through 316 and 321 in this presentation. There is a new range, EU range, which has superseded it, but I will stick with 304, 316, 321. Right, as I've said, enormous range of grades of stainless steel, some developed for specific applications. But fortunately for the brewing industry, the majority of applications are these, what I've called run-of-the-mill, 304, 316, 321. These are known as austenitic grades. All these grades are related to the crystalline structure. There are 4 other forms: ferritic, martensitic, duplex, and precipitation hardened. Austenitic is particularly useful as it is non-magnetic. As I say, fortunately for brewing, most of the liquids and gases that stainless steel comes into contact with, it offers a good long-lasting resistance. But some exceptions. Some exotic steels, like duplex steels, are used in calandras in brew houses where exposure to high chloride levels from sugars and syrups coupled with high temperatures would cause a degree of corrosion in normal stainless steel grains. To most people, stainless steel is considered as the universal corrosion-resistant material, but it isn't. There are one or two exceptions, as you'll see in a minute. This table here is a breakdown of the normal grades. Unfortunately, the pointer won't work on here. It works on all as soon as I move on here. What you've got, I'll come back to 303, but 304 to 304L, the only difference there is 0.02% carbon difference. Is the most common one that you find, or used to find in breweries, and there you can see the percentages of the appropriate elements that help to give it its appropriate properties. The 316, as you'll see there, it's got similar amounts of carbon, manganese, very similar amounts of chromium, but it's got molybdenum in it. Molybdenum, I can't say that. That is, I would think, the most preferred material of choice in breweries these days. It is slightly more expensive. And then you get 321, which is has got an element of titanium in. Going back to 303, it's a material which I haven't used in breweries, but apparently it's got good machining properties, but it's not very good for welding. Somebody here will no doubt tell me it's the case. And the significant element there is the sulfur. I've just put this up for completeness. This is the comparisons of the EN standards with the ASTM standards there. So, for example, 316 is now 1.4401, and that's the breakdown of it. Wouldn't expect you to remember that, but just gives you a flavour of the change. And the thing is, if you pick up a load of stainless steel, short of that number there, which is 316L, which is equivalent to the 1.4404, you don't know what it is. It's the only quick way of knowing what the grade of steel is. Otherwise, you'd have to go for a metallurgical testing in a lab. And this, again, is an idea. This is a non-bore 316 stainless steel. What I'm pointing out here is this is for really high pressure applications. You wouldn't normally use these applications in the brewery. The brewery can get away with the OD thin wall stuff, which is about 2.5 millimetres thick, and that will stand most of the pressures and temperatures that we want. Right. You saw in that table earlier there's the different elements, and what do these elements bring to the party? Well, the chromium provides the basic corrosion resistance. The molybdenum provides high temperature strength and increases corrosion resistance. Titanium promotes strong carbide formers. If I'm right, you see that was in the 321, and I believe that is quite good for machining properties. Nickel provides high temperature strength and ductility. Carbon is the carbide former and is a strengthener. The sulfur that we saw in that 303 does enable the structure to be machined more easily, but at the cost of lower corrosion resistance, and it doesn't take to welding to a higher standard. So, the differences of the stainless steel grades is measured in fractions of a percent, along with the addition or the emission of the elements. There are two examples here. The addition of the titanium in the 3-to-1 ups its resistance to corrosion at sustained high temperatures, as well as maintaining its tensile strength. This relatively new grade 303 performs better than 304 when expensive machining is required, but at the expense of some corrosion resistance, and it makes it how the sulfur content makes it unsuitable for welding. Stainless steel corrosion. A look at the maintenance, say, the stockist website shows an array. But in the corrosion in the brewing industry, it's either pitting or crevice corrosion or intergranular corrosion. There are really three types of corrosion. There's the physical, chemical, and microbiological corrosion which occurs under stainless steels, and one is in temperature, following being subject to high and low temperatures. There's associated with the chemicals, which is the chloride levels found in syrups and sugars, sulfur dioxide levels found in ciders. And there's one that I came across which was microbiological corrosion, with bugs eating the stainless steel, which sort of added them all. So high and low temperature corrosion. I've seen this where we've had cold CIBD centres put in using grade 304, and then the brewer thinking, well, I want it to be a hot CIBD because I can reduce the time of my CIBD regimes, have gone to hot CIBD and then ended up with corrosion. 316 would have been a better choice. Mentioned chloride levels, thought could be linked to high concentrations of chlorides and high temperatures found in sugars and syrups with work boiling calandria. And one of the Briggs calandrias that I bought was made with duplex steel to counteract the exposure to the high chloride levels and the relatively high temperatures. And one of the more recent nature is sulfur dioxide levels. Quite a few breweries now have taken to packaging ciders, and even at ambient temperature, the sulfur dioxide in ciders can cause corrosion of 304 and 304 grades, and to prevent this, 316 grade should be the only ones considered if you're using the use of sort of putting cider through your plant. Microbial corrosion. Not many people are aware of this corrosion. I experienced it in plates over at the Burton brewery a few years ago, or more than a few years ago, where there was an infrequently used plate pack that was sometimes left charged with water and other times rained down. But we had corrosion in these plates. We didn't really know what it was, but then a few years later, the Technical University of Denmark published a paper identifying the causes of the problems. And 304 and those three grades suffered corrosion failure in drinking water systems that they'd installed in Denmark. When they go beyond the microscope, they found it had been the microbes that had been jumping on the stainless steel, causing the failure. That failure mode is looks like pitting or crevice corrosion. This was, bear in mind, this is aimed at students doing exams, so probably you already know about this, but this was to point out that welding of stainless steel is really only able to be done sensibly and professionally in an inert gas, where the welding surfaces will be mechanically strong, you get a smooth joint, and it requires minimal grinding and polishing and the risk of any old traps. Gas welding must be undertaken for all grades of stainless steel, which are capable of welding, but not grade 303, as we said before. This was to highlight the effect of MIG welding in a competitor's fabrication shop, and that was just to highlight that welding quite a thick pipe onto the base shell of a vessel, and careful not to burn through the thinner material before the thicker one is welded too. Stainless steel surfaces and finishes. One of the things that brewers go for is a microbiologically bug-free finish. For stainless steels, irrespective of grade, the descaled internal finish is specified by most major brewers in their engineering standards. I know that Molson Coors and Bass use those. The descaled finish is obtained by as the pipe is drawn over a mandrel to steel mill, and has proved to give the smoothest and uniform internal finish. You'd think that polishing the inside of the pipework at the later stage would give a smoother finish. Well, it would in theory, but in practice it's been found that the polisher occasionally takes a gouge at the inner wall. This leaves a crevice which then is where bugs can set up home. Cost of stainless steel. I haven't put any figures on this other than saying A is cheaper and B is more expensive. The cost of stainless steel is really linked to the elements on the nut which are included therein, such as chromium and nickel and titanium. They to an extent determine the overall price of stainless steel, and these prices fluctuate daily. I'm going to say, I don't need to tell quite a few of them here, it can cause quite a problem between quotation dates and order placement dates. So contractors have to do a bit of crystal ball gauging to allow for material fluctuations in their quotes. But in the larger contracts, they have clauses to allow for price adjustments. As a general rule, 304 is the cheapest, followed by 316 and 321. Rather than 321 be more expensive than 316 more expensive than 321. And on occasion, 304 was cheaper than Renban mild steel. That was when I was doing some conversion of mild steel pipework to stainless steel, as being a long-term maintenance sort of saviour. When you consider the physical and chemical properties of stainless steel compared with other materials, it sometimes falls way short in some areas of desired attributes. But overall, stainless steel is considered a good all-rounder, and that's what you want. You know, there's always the pros and the cons, which I'll go through in the next few slides. Things that are going for stainless steel is a good tensile strength, which means it can withstand a fair amount of bending and breaking. Its elastic properties, things like linear objects such as wire rods and columns. We measure them as a ratio of the stress to the strain in the Young's modulus, and in the next slide you'll see the comparison. So here you've got this tensile strength, the modulus of elasticity and the normal strength, and there's stainless steel sitting top of the pile with 500 pascals strength. Copper is about half that. Aluminium is way down, and the only other thing which is similar is mild steel structural, but is really stainless steel is the best in that particular category. One of the things that you find in brewing is that you're either heating it up, cooling it down, or trying to keep it for a long period at the same temperature. And thermal conductivity is an important element. This is the ability to transfer heat from one platform to another. Now, here, stainless steel isn't the best. As the distillers know, copper has the best thermal conductivity, the ability to transfer heat from the heat source into the product. And from the table you'll see on the next, copper has got thermal conductivity of 400 watts per meter per Kelvin, and is brilliant compared to stainless steel, which has just got 16. As I said earlier, it is other properties that stainless steel encosts and make stainless steel preferred in these days. And just as a throwaway, some products like rock-wool insulation has got an incredibly poor conductivity, and it's used as an instrument. So there you go, there's this thermal conductivity table with copper heading the lead, stainless steel way down at 16, and mild steel is a little better, but it's one of the trade-off areas, but it's not as bad as it could be. You'll see why in a minute. There are other elements associated with thermal conductivity, and this is element called wettability. The boiling mode is affected by temperature difference, thermal conductivity, and surface wettability. With copper vessels, a clean copper surface is known as wettable, and the analogy of this is of low surface tension where the bubble forms on the surface, and it doesn't take much energy for that bubble to rise, go to the surface. Where, as I say, they're easily released, and the film boiling only occurs with a high delta T, high temperature difference. Problem is with copper that these surfaces soon attract solid deposits, and the boiling regime with a consequential reduction in evaporation, it falls off. And I've known that when I was running the brew house at Alloa Brewery, which had these lovely coppers. Clean them up, first brew, you've got incredible evaporation rates that you look for, but come to second or third brew, you've got this cavern under the copper, and the amount of energy you had to put in was quite significant to get the same evaporation. So, as I say, everything's a trade-off in this world. Stainless steel, on the other hand, its surface is known as non-wettable. The vapor bubbles clinging to the surface saying, I don't want to leave, I don't want to leave. But here, this film boiling occurs at a lower temperature, and you do get the bubble eventually leaving. Stainless steel surfaces do get coated, but they get coated at a much slower rate. So like I can relate to Alloa, we used to clean the coppers after every 6 to 7 brews. When I worked in other stainless steel breweries, which you found that we probably get away with 10 to 12 brews before we needed to put a clean through. Coefficient of expansion. This, I've included it. It's important, but the only thing there is to make sure that if you're having two materials, that they don't have very significantly different coefficients of expansion. Copper and stainless steel have very similar coefficients of expansion, but aluminium expands considerably greater. By the way, forget that word coefficient, it shouldn't be there. And this can be recognised in the packaging areas where keg filling, it is vital to get cool back on the kegs after sterilisation prior to filling, as you probably end up with prior to meter keg filling where they just refill them. The expanded cask with the keg closing and you get beer losses. In long runs of stainless steel pipework, steam pipework, especially mild steel, loops are introduced so that the expansion and contraction can be taken up. And where you get two dissimilar metals, like I say, you've got to take into account their different rates of expansion. Some of you might recognise this picture. It's the old Allied breweries, Bass, Gores, Molson Gores Brewery. But in the foreground, you've got these loops, and from the boiler house, which can't quite see the chimney of, they used to feed the bottling hall in Curzon Street, and that was getting on for 1,000 metres long. And there you see one of the expansions loops. They put in the admittedly it's mild steel to take up the expansion as the steam heated up or cooled down. And there were springs. There were also loops and springs in that assembly. You might think that was an expensive exercise to do it, but in fact, British Rail at the time was going to charge us a fee for taking full tankers over their railway line at Burton station. So we decided to put in a steam line and get rid of the tanker operation. These are some of the coefficients of expansion. As I mentioned, stainless steel and copper are very similar. Aluminium is quite a bit higher. It expands a lot more. And then you've got other elements like rubber, fiberglass and plastic. This is an example of insulation cladding being applied well and capped off well. Strange thing is, I don't know why they never insulated around the flanges. And in the foreground you've got a stainless steel flange, and the one rising underneath it is a mild steel flange. But their expansions are not too dissimilar. So that's all I've got to say about stainless steel. Moving on to mild or carbon steels, these are actually reducing. I mean, certainly when I was working, I was trying to get rid of mild steel in preference to stainless steel on maintenance grounds. Most of it these days is found in the utilities applications, steam, refrigeration, process gases and water, with a strong resistance to making sure that no mild steel comes into contact with any product. And brewery engineers are still trying to replace mild steel with stainless steel on the grounds of maintenance. You don't get any flaking of on internal pipe work, and you don't get any rust to contend with. This is an example of, these used to be what they had in Scotland. These were 5-barrel tanks installed in pubs and restaurants, and they were mild steel tanks, but they were lacquer-lined so that you didn't get any contamination with the product. And yeah, it was in the good old days when people drank beer, and it was the best way of keeping some pubs fed with beer. Moving on to sort of copper and metal and brass. You don't find many operations still using copper and brass in daily usage. Copper is a smashing material, as I'm sure you'll find McMillans would agree, to work with. It's so malleable, you can weld it, and you can polish to a very high degree, probably varnish it to retain that polished effect. One of the main downsides was its inability for the solder joints to withstand CIPs, the automatic CIPs, and you know, like for like comparison, it's quite expensive. The other side is that the internals do get heavily scaled up, and this reduces the heat transfer, and so it pushes your heating fuel costs up. An alloy of copper, and tin and zinc, and then gum metal, found its way into breweries in around about the 60s. And this was used in laserton plates. It was found to be quite easy to cast and machine, and it had a good resistance to all the products that were sort of thrown at it. But again, it's been superseded by stainless steel on cost grounds. There's a picture of an old decommissioned copper, and you can see where the you've got the failure of the solder at various points, leading to leakage. That one was in the Marston's brewery here in Burton, Colesberg Marston's. Is that right? Briggs. And this is the internals of a really ancient brewery. It's the Sarah Hughes brewery at Sedgley in the West Midlands. And there you can see it's got a copper mash tun with ceramic tiles round the edge. Still produces good beer. Aluminium, well, because of its poor resistance to caustic, it just corrodes away and you just end up with a pile of dust. You rarely find it in brewery process plants, and if you do, you must have big stickers around it saying, you know, caustic in this area. But the main areas with aluminium has been in the area of aluminium casks and keg trade, and some recent work undertaken in checking the internal finishes of such kit has found that even after 35 years in service, their internals were as good as new. But you've got this sort of connection of aluminium and Alzheimer's, so
there shouldn't be any aluminium casks in trade. It's illegal. They were taken off trade about 10 years ago.
I know.
So there shouldn't be any.
I found two in Shipley in Yorkshire, but that's another story. Yeah, you're absolutely right. But the other area that you can find aluminium being used is on the external cladding of insulated pipework. It does look good, but it's easy and it's easy to form, but and it's slightly cheaper than stainless steel. But if it gets damaged by some ladders resting up it or some other accident, it is prone to dents and it looks awful then. So for, I don't know what to put this one in. This is just a stainless steel cask on the left, side by side with an aluminium cask. Yeah, that's a rare picture. That is rare. Because there's not many left there, so it's two in Shipley. New Adams
Any cobalt don't exist anymore, are they?
And that's just one of the pictures of what you find in keg repair areas where the chimes of an aluminium cask was being damaged and it's going away for scrap. That was a picture of mine taken 19 years ago. Okay. Plastics. Well, these have really come on in leaps and bounds, and like stainless steel, like mild steel, the range is just enormous. There are two main groups of plastics. You probably all know that. There's the thermoplastic and there's the thermosetting plastic. They behave differently when exposed to heat. Thermoplastics just melt under heat, whilst the thermosetting plastics retain their form and stay solid under the heat once cured. There was always this concern about taint and pick up and low resistance to high temperatures with plastic containers. But these problems seems to have been overcome now with the new eco-coats coming on the scene as competitors to stainless steel in terms of cost, resilience, damage, weight, and I suppose I should put on there theft. In production areas, plastics have also been applied to linings of existing tanks, like open fermenters and a few dosing pumps. Pipework is not, plastic pipework is not necessarily found in many areas, production areas of breweries, but it can be found around softening plants and the like. This is the internal of a plastic line BFBi at what was Wolverhampton and Dudley's Wolverhampton Brewery. They had lined some FVs and they said to increase their life dramatically. High density polypropylene has become widely used in breweries, not only for large applications such as salt saturation tanks and hazardous materials, but also used because of its low coefficient of friction in noise reduction, applying them to strips within stainless steel packaging conveyors and side arms, especially can twists, which have superseded what used to be the old stainless steel ones. But as with all things, there can be a downside, and that in some coloured cans, especially dark blue, they can leave their imprint on the polystyrene strips. It's almost like the ink that was used never dries onto the lacquer, and so you can get the strip stains and you lose some of the intensity of the colour. But other colours are 5 minutes. 5 minutes. Oh right. Okay. That's a high density polypropylene bulk caustic tanks at Carlsberg. It's got its own self-contained bund. It's out in the sunlight, it's out in all weathers, and it's still there today. It seems to be a good one. And that's a salt saturator. And that's a Wilden pump. You've probably seen those round by East transfer pumps, and one of the beauties of that is you can actually see the product going through the pipework. We're getting close to the end now. Wood, it used to be all around the breweries. It's easy to reuse, it's easy to work, it does deteriorate quicker than metals, and its decline came at the expense of metals, but it was a good product. An interesting fact is that the choice of wood nowadays is confined to the European oak, which is sourced in areas in Europe which saw no military campaigns during the two world wars. And the reason was that there was no risk of bullets or shrapnel lodged in the tree, because otherwise it would render the trunk useless for cooper work. There's a picture of the cutaway section of the Burton Union system with the wood cask. And this is an etching of the Marston Burton wood union system. And that's a wood clad mash done at the Syracuse brewery in Edgeley. Rubber, normally found in hoses and gasket materials again. Numerous grades of rubber available. The thing you've got to go for is food grade, which indicates they're tank free. Other areas you might find large uses of rubber are in the CO2 carbon dioxide recovery balloons to collect the CO2 prior to the CO2 gas going forward in the plant to be processed as the gas. And the other one is rubber lining of some tanks, usually storing concentrated acids. So this is a picture I took on one of my holidays in the Cayman Islands. We used to call these snake pits for obvious reasons. Food grade rubber hoses. This is because we have a typical hose with a reinforced stainless steel braiding and outside protective cover, good for durability, crack resistance and heat, aiding, but it doesn't take well to forklift trucks driving over them. It's also ideal for positive pressures and can withstand on occasion small negative pressures, but not recommended. Slate, a few slate line fermenters in operation. It's good clean surface rendering itself. It can be cleaned effectively, and it's reasonably easy to work, but the joints can be a problem. And this is an old picture of a slate fermenter. I believe it was at Wolverhampton Dudley's brewery a few years back. I've left glass till the end. Its use in beer production is somewhat limited. You can usually find it naturally in the laboratories and in the first stages of yeast propagation, but the bulk of it is found in bottling lines, and transition from crock pots to glass came about with the mass production of the bottles. And this is the thing I've not found the actual effect of, but it's with either good luck or knowledge beforehand. The old brewers of old must have gone for dark glass, be it brown or green, as they knew the effect of sunlight affecting the smell and the taste of the beer if they left it in for a relatively short period of time. I've gone there to kind of sunstroke, and the substance produced is attacked by photolysis onto the alpha acids, forming a thiol, and it's their threshold, which is incredibly low. It's 0.01 to 2 micrograms per litre, which gives that skunky cat pee smell. And these are some pictures I've taken. One on the left is a sort of a modern take on crock beer bottle. The other one is a typical flip-top brown bottle, and the other one is wrapping it in paper to protect it from being sunstruck. And that was just a range of continental crown beers that are all in brown bottles. There's been this move to have clear flint glass bottles, and I know that Newcastle Brown used to sell their Nuki Brown in clear flint bottles, and I was never ever sure of the level of sunstruck problems that arose. And I worked there, and I asked them, do they get sunstruck? And I was told that the beer aroma and flavour of Nuki Brown masked any sunstruck off flavours. That is unofficial. It's now brewed in Chicago, and they actually put it in brown bottles. It's got a new recipe, but I'm not sure what they're doing with Tadcaster again. The thing about that is that I'm always nervous of beers that are in clear flint glass bottles stored in for sale in illuminated fridges in bars these days, as it's known it's light that stimulates this process. I've not found out whether it's a certain frequency of light on those refrigerators that prevents it. I don't know. The bottle on the right is one of the typical flint glass bottles. It's also a lightweight one, brought in to reduce transport costs, but it does give some problems of stability as they wobble down the transfer conveyors to the filler. What, you're off time?
No. to
There,
one time.
finished. Thank you very much indeed.